Okay, it is now 5:30 in South Africa, and we can start this webinar that will be presented by Mr. Frik-Jan of Rolls-Royce, Deutschland. It's my privilege to introduce the Aeronautical Society, which of South Africa, which is a division of the Royal Aeronautical Society in the UK. We're basically a fully fledged division of the Royal Aeronautical Society, and it was founded in 1911 by the late John Weston. It's a volunteer society with membership ranging from aerospace professionals, and corporates, companies, as well as enthusiastic amateurs. Registered at the Engineering Council of South Africa as a voluntary association and supports professional development of engineers and technical personnel to continue their professional development. We will also, for today's session, register the webinar attendance as for continuous professional development with AeSSA. Now, Aeronautical Society presents opportunity to individuals to exploit unique sources of inspiration. We try also to influence the course of progress in aviation and aviation-related subjects in South Africa, but also abroad by interacting with other companies and entities. We demonstrate commitment to professional development and career development in South Africa as well. Our links internationally is obviously with previous slide given, thank you, with the Royal Aeronautical Society in the UK, and then also the International Council of Aeronautical Sciences, or ICAS, and also the International Society of Air-Breathing Engines, AeSSA. Next slide, please. What we typically try to do is to organize local annual aerospace conference, and also to support outreaches, inspire the younger generations in terms of pathways into aerospace profession. And we also have an active lecture program that we try to do throughout the year, also as part of the continuous professional development of engineers. Now, Kevin suggested we do a couple of advertisements today as well of upcoming webinars. First one will be future developments in applied compressible gas dynamics, that will be presented by Dr. Randall Payton of Wits University. And the next one will be the presentation on Buccaneers of 24th Squadron, South African Air Force, that will be presented by Johan Conradi. So it will be quite interesting upcoming subjects that we will be presenting. Now, there is some particulars to join the Aeronautical Society if you're interested, and we are welcoming everyone basically to join the society and have some benefits from that as well. That's a bit old picture of our council, but it is basically mostly our council members, the current serving members, and thank you, Kevin, for that. Okay, I would like then to introduce Frik-Jan, that will be presenting the lecture today. Frik-Jan's career has been a colleague, ex-colleague of mine as well at Denel Aviation years ago. He's currently working in Rolls-Royce Deutschland in Germany. He started his aeronautical engineering career 26 years ago in the defense helicopter industry in South Africa. Before moving to civil gas turbine sector in Rolls-Royce 21 years ago, he's experienced full product development cycle from concept design to flight testing, and also entering into service of both airframes and propulsion systems. Along this journey, he developed from mechanical system integration to power plant integration of complex systems, including gas turbines like the BR710, BR725, the Rolls-Royce TAI 611, the Trent 1000, Trent XWB, the Pearl 15700 and 10X engines, also generators, nacelles and thrust reversers. For the last 2 years, he's been leading the hybrid electric power plant integration activities for upcoming flight demonstration of a hybrid electric system powered by a gas turbine. So we welcome Frik-Jan, and we're very pleased to have him presenting this lecture, and we are looking forward to that. Thank you, Frik-Jan.
Thank you very much for that introduction. Yeah, thank you for the opportunity to present. The presentation pack that I'll be sharing today is based on some of our company presentation material, but I'll be going into some more detail in the specific projects that we're currently involved with, but also the generic strategy that we're following on this journey to electrify the aerospace segment. So the first question that we're usually faced with is the question, Rolls-Royce, a lot of people understand and know us from our civil and defense gas turbine businesses, but it's not very commonly known that Rolls-Royce in its portfolio actually has a very long history around electrification of products, which goes all the way through to our civil marine business, where we've actually provided full hybrid electric power systems to anything from cruise ships down to luxury yachts. We recently sold that civil marine business, but we retained the electrical portion of that, and we're still working very closely with Kongsberg, who bought that segment. Yeah, you can see that there's two pictures, and we have the number of systems that's in development and also in the market. Similarly, with our Rolls-Royce Power Systems division, Friedrichshafen here in Germany, we do hybrid electric systems for complete trains and also do microgrids. So you can see that there's what we're having at the moment is this situation. We're taking the technology out of these market segments and bring it into the aerospace domain. And that actually gives us quite a number of unique capabilities, because on the journey to electrification, we're really, I wouldn't say rewriting the textbooks, but we are basically opening up a huge amount of opportunities to really redefine aerospace propulsion systems, but also redefine the platforms, because we can apply where in the past we had thermal engines. We're also bringing battery systems, high voltage battery systems, and hydrogen fuel cells into the mix. So suddenly you have a situation where you not only have the traditional thermal engine to provide energy, you also can combine that in a number of different ways with batteries and hydrogen fuel cells. In the middle, which is one of the key aspects, is the power distribution and the protection systems, fault protection and the power conversion. So, again, working from alternating current and distributing that through the platform in the safe possible way. but also in a way that actually makes it possible to meet the earth and lightning and EMC requirements that we have on a platform, which is quite different from something that we have in the industry today. And we combine those two aspects, or those two groups of technologies, and bring it then forward onto different platforms. Now you can see there on the right-hand side some pictures of some of the platforms that we already introduced. There's two ones in there specifically that we, in the aerospace sector. The one is the hybrid electric flight demonstration system that I'm leading the team here in Germany, which you can see in the top left-hand corner of that box. And then on the bottom right-hand corner of the box is some very schematic representations of Team Tempest's activities on the 6th generator fighter program in the UK, where Rolls-Royce is leading the power distribution and power generation platform. So the key aspect for us on this journey is that we bring technology in that can be really scalable and modular. So we can bring, systems to the market, and we have to bring systems to the market from component level through to subsystems and complete full systems. And there's quite a wide range just in those pictures on the right-hand side. We're ranging from 100 kilowatts through to the 5-6 megawatt type solutions in those ranges. So it's a very broad range of applications. And we're trying to bring our technology in to make that really scalable and modular to allow us to apply to the widest number of potential platforms. So why are we doing this? There's a huge move in the US and the EU to push the so-called Green Deal forward. And we have the very, very aggressive targets from both the EU Green Deal, but also from the ICAO to reduce the CO2 footprint of aviation dramatically until 2030 in the case of the EU Green Deal, and 2050 in the case of the ICAO package. And we believe very strongly that we have the opportunity here to bring this disruptive technology into the market. We're seeing a very strong trend towards mega cities with the continued population growth. We're seeing a lot of challenges specifically on the short-range regional transport market, where there's a huge amount of push politically to get to CO neutral means of transport. But we also see that in a lot of the European countries, eastern and western seaboard from the US and the Asian space, that the infrastructure is just reaching its limits. It's very difficult, becomes extremely difficult to put more traffic onto roads. Specifically in Europe, it's very, very difficult to put additional rail links in place. There's a huge, long bureaucracy process to do so. So we're trying to reinvigorate the regional air market to look at opportunities to bring that sub 500 nautical mile segment back to life in a CO2 or very low CO2 footprint or near zero CO2 manner. We're also seeing the fact that electrification is opening doors on platforms design. So there's a picture there of the Airbus or the city Airbus UAM, urban air mobility concept that is flying. That platform includes 8 Rolls-Royce electric propulsors, power electronic systems. And we're seeing, say, really a huge opportunity, almost a once in a lifetime opportunity to reimagine what flying platforms could look like. There's also a very strong push in those new platforms to make sure that we put gains in efficiency, emission reduction in place. But it's also what we're seeing is a very dramatic change in the number of players in the market. We are used to work with basically 6 large airframe companies around the world. But in the UAM market, we are confronted with over 200 startups with different level of funding and maturity, and almost as many concepts. And it's not yet clear which one of those concepts will actually be the ones that successfully enter the market. So it's a very dynamic market space. that are offering us quite a lot of opportunities. So from our side, we see that there's, we have two unique capabilities that we need, and that's what is needed in this market. On the right-hand side, we have component technology. Now, one of the really interesting or eye-opening aspects is if you look at world records power density on electric systems that you typically find in the Formula E environment. We're currently looking at, for example, electric machines around the 6 kilowatt per kilogram type power density. We are looking to inject technology in terms of component design changes, new lightweight materials, to really push the needle forward there. So we're talking about almost a factor 2 increase of power density that would be needed to deliver the requirements of, or to deliver a competitive platform. Similarly, what's happening in the electrical space, again, when you try to introduce or combine the electrical system with gas turbines, there's a huge push towards higher temperature materials in that domain, and also very simply actually qualifying a lot of the electrical materials for the aerospace market, because a lot of them, most of them, are simply not available through aerospace supply chains. And then the last item very strongly focusing on is fault tolerant design. Clearly, if you start doing numerical fault trees or platform level or these propulsion system levels, there's different ways to actually get to the rate that you need to be flying. However, we're seeing that a lot of that involves with redundancy, but redundancy brings a lot of weight. So we're looking at ways of actually putting fault tolerance into the electric machines, the power electronics in the machines, so that we can operate these machines. Today, a lot of them are very digital. They're either 100% available, they're not available. Looking at these fault tolerant design methods to actually make them operate at different levels, potentially reduced power levels when they do have specific failures. That's one aspect where we're building on our team, our strong team globally, pushing that forward, pushing that industry, the aerospace industry technology forward, and also bringing the whole aerospace materials approval and certification process onto those components. The other extremely important aspect is systems integration. There's a lot of experience out there on complex software. There's a lot of experience there on complex mechanical systems. And what we're doing here is we're bringing those two aspects together in one system integration activity. It's interesting because that also involves lots of tool development, because again, a lot of the classical software system integration tools are very centric around things like SysML, which is really software driven. And when you try to use those type of tools to model mechanical systems and combining it with the software systems, it becomes very interesting very quickly. But we're bringing that whole aspect and thinking on the safety and certification side of it. There's a huge dynamics around the certification requirement development at the moment through various ASME, also ASTM and EuroCai committees working in that space. And the AeSSA published the first edition of the Special Conditions E19, which will be the future certification rules for electric hybrid systems a couple of weeks ago. And we are, as a company, extremely actively working to develop those certification requirements with them. I've already touched on systems integration, specifically in this case, electromechanical integration. My journey here started a couple of years ago when we integrated a very high power generator for special missions onto one of our commercial platforms. And that very quickly showed us how, what the problems are when you bring that very fast reacting electrical system that has a lot of what was up to that point unknown natural frequencies and behaviors in the failure modes into such a mechanical system. So that's where we see one of our strengths. And then of course the other aspect is thermal management. With such a large number of components and also the integration of a gas turbine, electric machine and power electronics is quite an interesting challenge to get the thermal package clean and effective, but also to be fault tolerant, again, for failure modes. And lastly, but not least, controls. Just creating control systems with design assurance level A or B in many cases, is again one of our experiences that's needed to do this. And that's specifically where we see on a lot of the startups, the big deficit is understanding of what it takes to do these complex software integration packages. Right, so where do we think? We believe strongly that this this market will be dipping from the bottom. It's very clear when you look at wide body aircraft and large biz jets. Just reflecting, you mentioned previously some of the programs we involved. You reflect on a BR725 engine on a Gulfstream 650. When we run that on a test bed here, we're generating 18 megawatts of shaft power on that gas turbine. Now, if you imagine what the size of an 18 megawatt electrical system today, it's very clear that there's a long road to travel before we try and get to that power levels. But in that segment, we're already seeing today a very strong push towards the more electric engine and the more electric aircraft platforms. The Boeing 787 was one of the first ones. There's after that program and some of the complications it had, there's a bit of a lull, but we now see a very strong push again in the next generation of platforms towards more electric. And in this case, really embedding the electric machines into the gas turbine. There's a picture on the middle, on the bottom there, showing an AeSSA engine that we recently ran in Bristol that has a fully embedded generation system on its HP spool. We actually ran a second generation of that with a embedded generator on the LP spool. And the moment you have that capability, you then start to have really interesting options to transfer power between spools, but also to augment with electrical power from outside during specific critical flight phases. So again, it opens up the design space quite significantly. As we then go down, we start looking into regional commuter aircraft, where we're seeing very strongly that the hybrid electric options will be what leads the market there. Clearly, the power density from a gas turbine, combining that into a turbo generator, we see that has a really big advantage. And we believe the first generation will be of hybrid electric systems around those gas turbine powered turbo generators. We are, however, very optimistic about the future for fuel cells. They are at a much lower maturity, specifically if you start talking about taking complex fuel cells to high altitudes. But that is the journey that's currently being worked. And then as we move down to the bottom end of the market, or the smallest end of the market, the small propeller market or urban air mobility, there we believe the initial applications will be all electric. They will be short range. And they will be specifically in the urban air mobility market and small propeller market. Again, there will be a sub-market group there where we will go into the hybrid electric solutions. So there is a clear cascade here that we believe we will follow. And we are focusing our projects to support those different market segments and timelines. So when we talk about small propeller aircraft, these are typical the 1 to 4 seaters, CS22 type aircraft, where we're seeing that noise is a major driver. Specifically here again in the US and the EU, there's very significant noise restrictions that limit the operation of these aircraft. So breaking through those or through those noise limits, basically getting the propulsion system to a level where it operates well below those limitations, basically enables those platforms to fly many more hours. But also low emissions, specifically smaller platforms that are landing at airports close to cities. We're seeing a big push towards that. There's also, interestingly enough, from a lot of training organizations, both civil and defense organizations, a push towards low emission training. So we see a really good market there, and we're talking about that's a 50 to 300 kilowatt type market. And again, we're talking about first products early in the second half of this decade already. So you're looking at 26 to 28 for market entry. Urban air mobility, and this is a really exciting prospect. It's an incredibly large opportunity in the market. And again, there's this, the market is split between the so-called intercity, i.e. taking the e-taxi from the local airport down to the city center. There we see all electric applications. But at the moment you start flying between short range city pairs, Berlin-Hamburg, for example, or Berlin-Dresden, you start talking about hybrid electric solutions. And that's a complete new market, and it's very important for us that we drive the lowest possible CO2 footprint in that market creation. Typically, those systems are below the 1 megawatt type range. At the moment, most of them are on around 4 seats. And you may be aware that Rolls-Royce has actually signed contracts in supporting specifically vertical aerospace in this domain. We're very excited to actually support them and put our systems onto those platforms in the very near future. Again, entering to service in the 25 to 27 time frame. However, we need to be very clear. There's a huge amount of work that needs to be done on air traffic control. There's a huge amount of work to be done on certification rules. And again, low noise and low emissions will be the key, specifically in large urban centers, to allow these type of platforms to fly in the city centers. We're looking at plus noise platforms for a 300 feet flyover of well below 60 dB, which is less noisy than a double-decker bus riding past you. And of course, we also need to get the safety right. The consequence here in terms of passengers may not be that high, but it's going to be a very difficult environment to do any type of emergency landings or very, very actually applying very stringent rules in that market, more akin to CS25 than to CS23 or CS22. Then again, future markets, mentioned this before, up to 19 seaters. They're interesting. We see a huge pull from a number of, you could potentially call them niche market operators, but we have, for example, we're working with an airline in Norway, Widerøe. They operate a very large fleet of 20 seaters, literally hopping from one across the fjord. And there's a huge push on their side to get that all CO2 neutral within this decade. So we are in a partnership with Widerøe and Tecnam to convert and some existing aircraft, and also pushing the new applications on new markets forward. And then we actually, again, as I said before, really trying to reinvigorate this whole regional air transport market. Again, to try, and the key to that will be to be CO2 neutral or very low CO2. So these platforms, as I mentioned before, typically below 19 seats to the CS23 regs, and roughly around the 2 megawatt at platform level. And as we mentioned before, Rolls-Royce is active in all 3 of these markets, and we will be delivering, looking to deliver product into this market space within this decade. Right. So on the component side, we're seeing a lot of challenges. You may be aware that, for example, on the electric machine side, we are currently running a 2.5 megawatt electrical generator system that was originally designed for the eFan-X program. So we're powering that with a AE2100 gas turbine and generating 2.5 megawatt from that. It's an incredibly complex or compact machine, really high power density levels. But that machine is a, if you want to call it, was designed around the rotating shaft speeds that was available from the 2100, and is clearly designed as an additional, if you want to call it, unit that you drive from the propeller gearbox. The next step now is to embed those electrical machines fully into the gas turbine, different thermal environment, different speeds, sharing oil systems, sharing cooling systems, potentially sharing control systems to really get the power densities up. On electric controls, we mentioned already, so we haven't get a really unique challenge here, because the control systems for specifically power conversion units, digital rectifiers and inverters, run at immense high frequencies, switching frequencies up to 2 kilohertz, powering them through solid-state silicon carbide switches. So again, it's a very novel industry application that we're bringing in and trying to push the integration to the system, and to push up not only the power density but also the reliability of these units. On energy storage, obviously currently the current generation of lithium-ion cells comes with quite a number of challenges. There's a new certification rule set, DO311, that specifically look at battery systems, and yeah, we are currently testing probably the 3rd generation of battery systems for aerospace and Rolls-Royce that are fully compliant with DO311, and it's been a very interesting learning journey for us. This one is very visible, of course. There's been a number of very highly visible events at some of our competitors, at test beds with battery fires. So that's something that we're treating very seriously and trying to apply really robust and NLR principles to the way that we integrate those battery cells into packages. Electrical systems, I think I'm not going to go into too much detail there. I mentioned that before. You know, it's the ability to actually integrate it all into a power plant. And again, power conversion, the key message for us, or the key activity there, is to make sure that we have scalable modular systems that we can deploy, as you saw in our previous market, any from 100 kilowatts up to, you know, the multiple megawatt class range. Right, so if I move on to some of the applications. So this is just an overview of actually the platforms that we are currently flying on experimental basis. So you can see there, it starts off with the classical a Magnus E fusion aircraft, CS22 aircraft below 800 kilograms there. It goes on to the extra 330 LE. That aircraft is parked just around the corner from us here in Strausberg. A company called ARPAS is one of our partners. It's the previous world record speed holder for electric flight. It flew 330 kilometers an hour, something. And we're preparing that aircraft for a 2nd iteration with an updated system and a new battery system for flight testing. Then we also have things like the flight design, F2E. Again, that aircraft just went through a flight test program, looking towards production. But there's also, for example, on the hybrid side, a very interesting system with Tecnam on the H3PS. We've actually introduced a small hybrid system as a booster onto a Rotax engine to increase power delivery during takeoff, but also cruise, enable the opportunity to actually cruise all electric and optimize against CO2 and noise. Aerospace Flyer is another platform that we had flying until about the end of last year. So the Airbus I've mentioned before. So again, you know, that platform. So although you can see there are 4 grouped propulsors, they're actually stacked on top of each other. So there's a total of 8 electric machines there. And that platform did a number of flying hours in Ottobrunn in Munich, and is actually still continuing flying at this point. Tecnam P-Volt, again, as I mentioned before, specifically with Biederer, we're working there to look at an all-electric short-range flying aircraft. And then we had a demonstrator program converting a Dornier 228 with 2 electric machines on an all-electric basis, and then on the right-hand side, bottom right-hand side, the current hybrid electric demonstrator that we're working on in the ARPAS I5. And I'll be talking about that specific program on the next foils. Yeah, so the purpose of this program is really to be, firstly, our flagship. You know, this is the most complex hybrid electric system that's being worked in the industry today. It has a gas turbine, high voltage battery system in it. We defined the program to really investigate a number of aspects that a lot of articles are written about and claim some benefit, very few have actually demonstrated. So we started things like just investigating, you know, it's designed to investigate certain aspects of distributed propulsion. This platform will also have extremely slow turning propellers. So we have 9-bladed propellers turning at 900 RPM. All our noise calculations tells us that we're going to be around the 20 dB mark on those propellers. So again, enabling really quiet operation of the platform. Similarly, with the embedded gas turbine, we've installed some new patented noise reduction technologies to get the gas turbine noise down. And we're basically looking at the whole aspect. We're trying to do, if you want to call it almost we're using a flight clearance investigation program instead of a type investigation program. So we basically designed the flight clearance program as if we are certifying the platform and agreed that 100% with the local authorities here in Germany, the LBA, the Luftfahrtbundesamt, with the intention to actually practice and test what it takes to certify a hybrid electric system. This program is being worked in partnership with, again, the company called AeSSA and the Brandenburg University of Technology in Cottbus. And we're being very strongly supported by the local state government here in Brandenburg. If we look at the breakdown, so that's a map of Brandenburg that you see there with Berlin as an island in the middle. So we at Rolls-Royce, through our anchor location here in Dahlewitz, we are doing the whole power plant integration. So bringing the electric system that is coming from Indianapolis, where they're doing system integration, distribution protection, some of the control system. We then bring the generator that's being done by our site in Trondheim into play. Our team in Singapore is doing the power electronics and the energy storage system, and our team in Budapest is doing the electric propulsion unit motor. And as I say, we bring all of that together in Dahlewitz into a power plant. AeSSA is a small company that specializes in prototype manufacturing and previously also doing SDCs, conversions of airframes. They are helping us with the integration of the platform, but they also be building the Ironbird and the actual flying airframe for us. We did a lot of work with them to see if it's worthwhile converting an existing platform, but ended up in the end designing a really dedicated platform for us. And lastly, BTU Cottbus, who's supporting us specifically on the safety side, but also doing a lot of work on us on the system modeling side and the test support. Yeah, our clear project charter on this case, is absolutely number one is safety, both electrical safety and safety of flight. We are very conscious that in the CS22 and CS23 environment, the regs do not force you to do numeric safety assessments. It only requires qualitative safety assessments. And what we're doing in this space, we are doing a numeric safety assessment, which is quite a challenge because it's really pushing the data availability for the electric systems very hard. Of course, there are some legacy data available through mill handbooks and other places, but the reality is that there's not a lot of industry experience, even with permanent magnet machines and solid state switching power converters. So we're bringing those two aspects very strongly into the integration part. And on the power plant, for example, what we're doing here is a piece of work that defines the cockpit interface. So we literally own everything through the throttle leaders and the interface, and we're trying to define and support industry standard indications for hybrid electric systems, because that's something that is currently does not exist. Integration with the platform, I mentioned a number of times. Thermal management is a huge challenge with our distributed system. Noise treatment we've mentioned, distributed propulsion benefits mentioned. And again, as I mentioned, the development of the certification understanding and really practicing what it will take, learning what it takes to certify a system like this. So we're doing this in 4 steps. We're having the component level activities, as I've mentioned before, distributed around our global team. That will basically peak in a component rig test campaign around DO160 to look at qualification and test of a lot of the individual units and making sure that we get the FMICAs for those units sorted out. We then bring that system together as a propulsion system where we integrate the electrical system. We were testing that on a Copperbird facility. We have a facility in the US in Indianapolis, but also one in Cottbus that we'll be using. And then the next step is an Ironbird, classically bringing all the platform integration components into there. So power gearbox, the propellers with the pitch control mechanism, the installation, the inlet, the exhaust, putting all of that together. And basically the Ironbird is an aircraft without outer wing and tail pieces. And then finally, in 2023, the aim is to go and fly on our aircraft level demonstrator and we will be doing a roughly 200-hour platform flight test program to investigate a number of items on that operability, but also on how you operate such a complex system, and confirming the basic performance parameters on the platform. Interesting, what I want to notice on the Copperbird, we will also be doing a very novel approach in terms of doing actual fault injection into the electric system. Now that's something that is quite common on control systems, but it's something that's not very common and hasn't really been done before on high voltage electric systems. So we will be, based on our FAMICA or full from the platform down FHA, which by the way, we've created a model-based systems engineering model from the platform level down to the propulsion system, the power plant propulsion system, down to components. We've synchronized and aligned that with our safety assessment, so we have a really strong model to understand how functionality and failures propagate through our system, and based on that, we've defined this fault injection testing. So it's going to be quite an interesting time. Obviously, high risk of actually doing some damage to some of the units, which is already planned in. But yeah, really making sure that we understand and can simulate not only the performance of the unit on a blue sky day, but also actually can model and simulate the failure of the unit and validate those test points with data. So here's a short view of that system on the platform, and it gives you an idea of the complexity. We start off at the back with a M250 gas turbine, so we're using the strongest variant of the M250 system as an initial starting point. In front of that, which is not quite visible, there is a high-speed generation system. It's basically 4 electrical generators in one that feed through into the 4 rectifiers that you see in front. Again, so this is quite a, if you want to call it, standard approach. We've not, in this case, for the first generation system, gone for full integration with the gas turbine and the electrical systems. You know, that is something that we're working on, very focused for the second generation. But you can see here just the space claim that you have here when you compare the physical space of the gas turbine with the actual electrical system. What you also see on the top there is the a special inlet that was designed for the gas turbine that includes some patented noise reduction technology to get the gas turbine also below the 60 dB on that flyover point. So from the power electronics there, we then distribute the power through a distribution protection unit system. So again, high voltage solid state switches, and through that, through this red network, we distribute the DC power through the aircraft. So that system is running at just over 1,000 volts. So again, that's quite new and novel for an airframe platform. So aspects of everything from earth and lightning, bonding, how you deal with short circuits, etc., is very challenging in a very lightweight composite airframe. But that was one of the ideas. But even things like finding a connector that allows you to install that type of voltage to a box doesn't exist. So we've actually gone out with suppliers to actually create new standard of connectors and plugs to do this. So from that distribution system forward, you can see there's some of our controllers, some of our dedicated low voltage batteries, the engine controllers, and we then distribute the power out to, in a redundant bus system, to the 4 propulsors. So again, you've got the power electronics, which is exactly the same power electronics as there, but just working in reverse mode. So over here, they're a rectifier, in here, they're an inverter, then driving a high-speed electric machine through a power gearbox, and then driving these 9-blade low-speed propellers. 4 of those distributed. At the back end, you can see here our battery packs. So we've basically designed, as I said previously, the DO311 compliant battery packs. To give you an idea, those battery packs are, we look at energy capacity are around 45 kilowatt hours. So they're actually very significant batteries. But if you compare again with the energy that we have in the kerosene, it actually provides only a small fraction of the energy on the platform. But it again allows us to do lots of novel optimization work on the airframe. So for example, during a climb, we would start off at a certain climb power, and then now we have the option. You can either boost the power at climb to reduce your takeoff distance, or for example, you can, as you climb out in altitude and the gas turbine performance start to drop, you can actually top it up with the electrical power to give you a much faster rate of climb to get to your cruising altitude earlier. We're also doing, for the redundancy, system specifically was designed such that if we lost the gas turbine at V1, there's enough power and energy in the battery system to continue the climb out, get to a safe circuit altitude, and do a landing, a powered landing on the aircraft. And then, of course, as we mentioned before, with the redundancy in the buses, we can tolerate failure. So, for example, we can lose one complete power bus and still operate the aircraft safely without any problems. So we've done a lot of work there on our fault tree analysis to make sure that we can actually get to failure rates that are acceptable to continue to flight this program. So if we then look at one of the interesting aspects of this, if you look at the system distributed, when you look at the aircraft, you can see we are taking up a lot of real estate on that platform. And of course, that's one of the key aspects for the second generation and production systems, again, is really tightly packaging those systems, integrating those systems to make sure that we end up consuming a lot less real estate on this platform to give it the cargo and payload capability that it needs. Right, so that's in a short nutshell, the key activities. As I say, I'm leading this program here in Germany. It's been a really interesting journey. Looking forward towards the 2023 timeframe, we're going to fly with this system. But I just wanted to mention that we are working with a very strong group of universities as well, specifically here in Germany. I mentioned the Brandenburg Technical University in Cottbus a number of times. We also got very strong ties to the Technical University in Dresden, the Karlsruhe Institute of Technology. Now those three ones are the university technology centers for Rolls-Royce in Germany. On the right-hand side, all three of them are UTCs for gas turbine activities. We are now expanding on that into the electrical space. If you look at the right-hand side, you can see there's the 4 UTCs that we currently have specifically for electrical work. But as I say, we are very strongly pushing onto BTU Cottbus, TU Dresden, and KIT to expand that envelope. But we're also active in Nottingham, specifically in Norway, Budapest, but also places like Nanyang Technology University in Singapore. So again, we're fortunate that we have a very, very strong network, a very strong global network, and a very strong pool of people to pull on, experience to pull on, to bring us forward on this journey. So with that, I would like to end the presentation and potentially hand back to Kevin or Gert to open the question and answer session.
Yeah, well, thank you very much, Frik-Jan, for the most interesting presentation, and yeah, just for the details and of a very, very leading edge work that you're doing. I mean, this is like moving into a whole new technology domain and trying to figure out what it is to what is the optimal way of doing things all over again. And that's a very exciting space to be in. Just as an announcement to everybody, please just type in your questions, and there's a Q&A function at the bottom of your screen. Just go in there and type in your question, and then Frik-Jan can respond to them one at a time. So going on from that, so Frik-Jan, thank you very much for being willing to speak to us all the way from Germany. It's been very informative, and we really appreciate the time that you've taken to speak to us and to enlighten us, because certainly as aeronautical engineers and as people working in the aviation sector, I think we're going to be seeing the fruit of your work in our workplace quite soon. So this is This is a very timely presentation. Okay, so we have one question so far from Graham Garton, and he says, how do you see the world keeping up with being able to deliver power to charge batteries in the pure battery world, or the hydrogen fuel cells to keep that power generation clean in line with the zero carbon emission requirement? So how do we generate power with zero carbon emissions?
So it's quite interesting. That is really in focus at this point in time. We're actually seeing, specifically in the EU and here in Germany and Brandenburg as well, there's such a massive capacity that's been created for solar energy and for wind energy that in normal days there is actually more, for example, the state of Brandenburg can cover its complete electrical energy supply purely from those two sources. Of course, weather permitting, you do get days where the sun's not shining, you do get days where the wind's not blowing. But what's happening, for example, specifically overnight, is that a lot of the wind farms are actively switched off because there's no consumers for that electricity. So the proposal that's being actively worked is actually to do what's so-called PTX, power to liquids, so that we actually use those environmentally friendly power generation systems that are doing the off-peak power periods at night, that they will be generating and creating hydrogen that can then be placed into the gas distribution network that we have around Europe or some of the locations in the world to do that. So there's very active work, and a lot of the work that we are doing is in very close collaboration with large companies and large players in the green energy field, because that is key. There's two aspects there. Firstly, also when we talk about large aircraft with sustainable aviation fuel, it's a very similar discussion because there's very little of it around at the moment. How do we get to it? And the key message will be that we are actually working on tying into the green energy sector, and also looking, as I mentioned before, using also power systems capability to do these microgrids. You may be aware that Rolls-Royce itself is also working on something that's called SMR, the small modular reactor, where we're basically taking the technology from pressurized water-cooled nuclear reactors that's Rolls-Royce has been developing and production for the Royal Navy submarine fleet. We're basically taking that technology into a distributed network. There's a very large activity around that, and then using again that energy to generate hydrogen and charging batteries. So it's a clear item, and we have to integrate very closely with the green energy movement out there.
Okay, thank you for that. Okay, the next question I have there is, is Rolls-Royce currently tracking the development of graphene improvement of batteries? That's from Randall Patton.
Yes, we are very active in a number of forums. I mean, we've made a very clear decision that we will not be developing battery cells. They're simply not the economy of scale. What we are doing is we're working very closely in a number of forums. There's the European Battery Alliance. In the UK, there's a number of there's a government funded program as well. And we're looking at pushing our requirements into those segments, because what we're seeing is that our requirements are in many cases really driven around power density. In other words, how fast can you extract power from the battery system rather than energy density. So we are tracking and working very closely with those battery initiatives in Europe and in the UK, and looking at that market. The obvious one that's very interesting is solid state batteries, silicon carbide batteries. But the reality is a lot of these things are quite far from being industrialized. I think the next one will be the lithium anode batteries, probably the next technology step that will become industrialized. And but we will be a consumer, or we're putting our requirements into those companies and R&D environments, and but we will be a consumer of what comes out of there. We will not be driving cell technology ourselves. Interesting on that, just around the corner from us, a certain Mr. Elon Musk is building the first gigafactory in Europe, and he's just extended that to include a battery cell manufacturing facility. So every time I drive from Rolls-Royce to AeSSA, I drive past that building site. And it's quite interesting to see the scale of that activity.
Okay, thank you. Okay, the next question is from Ashlyn Ramdas. Considering that hydrogen hybrid systems have been used in the automotive sector for some time, do you use automotive components that already have a history of component data, such as failure rate data?
Yes, we are working very closely with the automotive industry. Again, Rolls-Royce Power Systems actually has a joint venture with Daimler, and we are working with Daimler on those fuel cells. But again, if you look at the amount of hours, the amount of systems that are actually out there, it's still very early days. And the other thing is they're all, of course, stationary. So the power density pressure simply isn't there. So we are typically looking at power densities. Once we get the fuel cells around the 2.5 kilowatt per kilogram power density, they become really attractive. The reality is the automotive systems are rather closer to 0.5 to 1 kilowatts per kilogram. So again, we will have to push that technology quite some way before it becomes 100% relative. But yes, we are keeping our ears very close to that through our joint venture with Daimler, but also looking at some other partners. There are more partners out there that are interested. There's only a few actually that's really active in the aerospace market, but we are talking to a number of them because that's one of the key things. As I said before, these high density electric machines, power electronics, it's going to be a real challenge to get real failure rate data. I mean, we're in a very fortunate situation in our gas turbine business that we have more than 300 million flying hours and so on. We have incredibly good failure rate data from that, but we're going to have to follow some really novel approaches to generate failure rate data, at least for the initial in-service instruction.
Okay, I've got a couple of questions in the chat tab as well. So there's a question from Andre Kutsia, and he's asking, is there any expansion of this technology into the pure helicopter application area? Do you envisage any expansion in that direction?
Yes, we're definitely seeing a lot of interest. You may be aware that Robinson recently flew a all-electric version, I think, of the RR, I think it's a 66. So yes, there's a lot of people looking at that. Similar to eVTOLs, again, it's a very similar motivation why they want to do that. Yes, so we think there will be a lot of focus on that. Again, key items as power density and energy density, to look at range. And the other thing that's quite interesting is what we're seeing, for specifically these high cyclical batteries, is that the operating cost for a battery, although the electrical energy is relatively low cost, the actually cyclic life of some of these battery systems will be quite expensive if they don't only achieve the number of cycles that they currently do. So there's definitely activity in the domain. As we showed previously, we had the City Air, we powered the City Airbus. So we have a very close correlation of working with them, constantly talking to other people in that space. So there's a lot of activity there, but again, the question is going to be, when is the maturity there? When is the certification rules there? And for things like training missions, short range hops, things like that, I think they'll be the place where it is into the market first.
Okay, I've got a question from Renee Haas, and he says that the cooperation of Rolls-Royce with startups and universities was mentioned. Is this cooperation limited to countries in the European Union, or is there scope for cooperation further afield, like South Africa?
We are working with startups and companies all over the world. It's not just limited to the EU. I mean, of course, when we start looking at companies, we always need to establish, firstly, whether their concepts that they bring are technically credible. And then the second question you always ask is, do they actually bring the finances to have a realistic chance to deliver something to the market? So we are very open. we've had actually a number of discussions with one or two companies from South Africa already in the past, and there's nothing that's stopping us from working with them. But at the end of the day, specifically in the face of having so many opportunities, we have to be quite rigid in our assessments to say, does the technical concept work? Does the business case work? Because of course, even we only have a certain amount of resources and financial resources to spend, so we need to pick the right candidate. So, but as I say, there's nothing stopping us from working with companies also in South Africa. It's I guess the question would be, bring your concepts and we can talk.
Okay, well, thank you for that. That's all the question that I see on my platform, and I think we've already spent an hour, so I think we need to start wrapping up. So thank you very much for your presentation, for your insight, for your time. Thank you everybody for attending, and I see we had a good turnout. We've been having some severe load shedding in South Africa, so I think quite a few people that wanted to join us couldn't, and we will put out the recording for those people that couldn't join us. But thank you all for attending, and I'll be keeping a record of your attendance so you can claim CPD points from this webinar, and just look out for the invite for the next webinar in July. So with that.